This is Module 6 of the Cisco Networking Academy Introduction to Networks version 7.0 curriculum. This module deals with the data link layer. The data link layer is layer 2 of the OSI model and is responsible for putting data out onto the network via the physical layer, which is layer 1. So the data link layer is responsible for the communications between end device network cards. It allows the upper layer protocols to access the physical layer media and encapsulates layer 3 packets, IPv4 and IPv6, into layer 2 frames. It also performs error detection and rejects corrupt frames. The data link layer is the junction between the actual physical hardware and the logical IP addressing. The IEEE 802 LAN and MAN standards are specific to the type of network, whether it be Ethernet, wireless, wireless PAN networks, and many others. The data link layer actually consists of two sublayers. Logical link control, which, as you can see from the diagram, is the layer that is directly connected to the network, layer 3, where logical addressing takes place. And the MAC, or the media access control sublayer, where it connects directly to the physical, where the actual physical connections take place. The logical link control sublayer communicates between the networking software at the upper layers and the end device hardware at the lower layers. The MAC sublayer is responsible for the data encapsulation and media access control via the many different types of connections that it may have, either physical, being Ethernet or fiber, also wireless. The packets exchanged between two nodes may experience numerous data link layers and media transitions, such as the initial transition may be either wireless or wired. As it goes out of your facility, it may be wireless or possibly fiber or possibly cable. So there are many different types of media that the data may pass through going from end to end. The data link layer is the layer that is responsible for putting it into a format that the particular outgoing media can understand. At each hop along the path, a router performs four basic layer 2 functions. It accepts a frame from the network medium. It de-encapsulates it. As you may recall, routers work at layer 3. So as data comes in at layer 1, it strips off the layer 2 information to go to the layer 3. So it de-encapsulates the frame to expose the encapsulated packets being at layer 3. It then will re-encapsulate the packet into a new frame. So if it is going to a different type of media, it will encapsulate it with the proper header for that media. It may also provide a new frame check at the end of the frame because the data from the original header is no longer valid. It will then forward the new frame on the medium to the next network segment. The standards for the data link are controlled by multiple organizations. Data link layer protocols are defined by engineering organizations, such as the Institute for Electrical and Electronic Engineers, the IEEE, the International Telecommunications Union, ITU, the International Organizations for Standardization, the ISO, and the American National Standards Institute, ANSI. You may be familiar with many of these organizations already, as they provide standards not only for networking, but for manufacturing and many other types of machinery, products that you come in contact with. In a network, we normally have two types of topologies, physical and logical. The physical topology will show the physical connections and how devices are interconnected. It may also show the actual path through a building so that wires can be traced. The logical topology identifies the virtual connections between devices using device interfaces and IP addressing schemes. In the physical topology, you may also have notice of the length of the cable, the type of cable, the purpose of the cable, and the type of end connectors on the cable. Anything having to do with the physical construction of the network should be contained in the documentation for the physical topology. Anything dealing with the logical topology, such as IP addressing, port numbers, operating systems, should all be included in the documentation for the logical topology. As far as physical topologies, we basically use three main types. Point to point. This is the simplest and most common WAN topology. It consists of a permanent link for two endpoints. If you have one computer directly connected to another, it is considered point to point. You may buy a leased line that goes across the country or across the state. This would also be considered a point to point. Now, to make it clear, a point to point connection does not necessarily consist of only one wire. If you go through a service provider, when it gets to the service provider, it may go through additional routers, switches, and other types of networking equipment. So thinking of it in terms of being a single cable that goes from one endpoint to another is not practical. But the logical workings of the point-to-point connection is the same as if there was a single line connecting two computers together. In many designs, you will see the symbol for a cloud. The cloud represents a group of networking pieces of equipment that we do not know exactly what they are. We do not need to know exactly what they are. They are provided by the service provider. All we need to know is when I put data into one end of a point-to-point link, it comes out of the other end, such as when you make a telephone call. You are not really concerned with the type and the manufacturer of equipment that your telephone service provider provides. All you really care about is that when you make a phone call, does the person at the other end answer the phone? The next would be a hub and spoke. This is very similar to a star topology where a central site interconnects branch sites through point-to-point links. If we were to take a look at point-to-point, it would just be first one connection directly going over to another connection. A hub and spoke may have a central unit, whether it be a switch or some other device, and coming off of that, multiple hosts. This may also be referred to as a star topology. The problem with this type of topology is that you have a single point of failure directly in the middle. You may also have an extended type. This is normally referred to as an extended star, where one of the spokes comes off and connects to its own group. The extended star is very common in today's networking. A mesh topology, it provides high availability but requires every end system to be connected to every other end system, such as if I have 4 endpoints, each endpoint would be connected to each other endpoint. So as you can see, in this simple topology, each end host would have to have 3 connections to connect to the others. You can see how this would become very impractical if there was more than just these 4 connections. Because as the connections increase, such as 5 connections, each end device would have to have 4 cards or 4 NICs to connect to all the other devices. Many times you may have a partial mesh topology, such as a frame relay cloud. Although not as common as it was, it provides a good example for a partial mesh. In frame relay, we would buy a permanent virtualized circuit. If this was going to be full mesh, I would have to have 3 virtualized circuits. But as you can see, I have left one off at the bottom. So to connect from this host, which I will just label as A, to this host, which I will label as B, we would first have to go up through this other router and then down. So it's taking a path up through one and down to the other. Whereas the top router has connections to both, so it is full mesh, but the circuit as a whole is a partial mesh. Something like this also provides us problems when we establish our routing protocols, where we may have to shut off split horizon, which tries to stop us from having an inaccurate path. There are some businesses that need full mesh, such as in the United States, atomic power plants need full mesh so that in the event of some sort of catastrophe, any computer could shut down the reaction. The point-to-point physical topology directly connects 2 nodes. The nodes may not share the media with other hosts. Because all frames on the media can only travel to or from the 2 nodes, point-to-point WAN protocols can be very simple. because whatever we put into one end must come out of the other end. And as you can see in this diagram, we have the network cloud, which we do not have control over because it's part of the service provider's network. But we do not really need to know what is in the cloud as long as what we put in on node 1 comes out at node 2. Some of the other types of topologies, as we talked about the star, which is the hub and spoke, the extended star, a bus topology. This was very common when networks were first being put into place and coaxial cable was being used. At the end point of the cable, you had to have a resistor to terminate the end so that you had a complete electrical connection so that data would flow. The ring topology, which could either be token ring or fiber, was very common in the early days of networking. It was mainly used in manufacturing where we had to guarantee each device was able to get onto the network. So that if screws were being put into the doors on a manufacturing line at General Motors or Ford or another car company, you needed to make sure that the equipment that was putting in the screws was able to talk and take direction from the network at the appropriate time. So early Ethernet and legacy token ring technologies provide two additional topologies, both the bus and the ring. When we make communication, it could be either half duplex or full duplex. Half duplex only allows one device to send or receive at a time on a shared medium, such as if we were only using one pair of wires, we could send, we would have to stop sending so that the other system could then send data back to us. This is used on wireless LANs and legacy bus topologies with Ethernet hubs. Some of the latest wireless standards can use full duplex. Full duplex allows both devices to simultaneously transmit and receive on a shared medium. On an Ethernet connection, we would be using one pair of wires to send data and one pair of wires to receive data. Since they are totally separate pairs, the sending and receiving can operate at the same time. Today, most Ethernet switches operate in full duplex mode. If there is a need to set this to half duplex, it can be easily done within the operating system. Ethernet uses a contention-based access. All nodes operating in half duplex can compete for the use of the medium. Today, using modern switches, because we create a direct connection 90% of the time, we don't really have contention based as we did previously. Examples of contention based would be a carrier sense multiple access with collision detection, which is used on legacy bus topology Ethernet, or carrier sense multiple access with collision avoidance, as used on wireless LAN. Many people get confused by the long acronym of Carrier Sense Multiple Access with Collision Detection. It means that many people are on the same network. So if I had multiple computers connected into a device, and currently I was having a communication between A and C, but B would like to also communicate with C. First, B would have to wait until the carrier was free, carrier sense. We have 4 units all connecting to the same network, multiple access. And then, if by chance we had a collision of data, such as if all these were connected to a single cable instead of through a switch, it is possible that while A is communicating with C, both B and D would like to communicate with C. So when B and D recognize that there is no more traffic being sent on the carrier is free, they may both try to send data at the same time, resulting in a collision. Once a collision occurs, the devices send out a jam signal to tell all devices on the network that there has been a collision of data. Each device, in turn, sets a random timer. The time is always at random, and whoever timer runs out first now has the ability to send. Since they do not know if their timer was the first to run out, before sending data, they must return to a listen before send. They must listen to the network to make sure that no data is being sent on the carrier, meaning that one of the other systems, their timer ran out previously. Just because in this example, B and D were involved in the collision, it does not give them any kind of priority or rights to be the first one to send data. Wireless, if I have a host connecting to the wireless, other hosts can recognize that and wait until the frequency is cleared. But we may have another host at an extreme distance that cannot see the first conversation. So this host may also try sending data. This is collision avoidance, in that if I see data being transmitted, I try to avoid a collision. Sometimes that doesn't happen. Each unit, before they can actually send their data, must send a request to send signal to the access point, and the access point, if it's able to respond, will respond with a clear to send reply. Controlled access is deterministic, and this is a term that you may see many times. Deterministic access, where each node has its own time on the medium. Token ring passes a token from host to host. If the host has something to transmit, they modify the token and put it back out onto the network. Once the receiving system has received the data, they too modify the token so that the sending system knows that the data was received. When it comes back to the original sending system, they will clear the token and send it on to the next system. So each node, each host in the token ring is able to send data. This is used on the legacy networks such as Token Ring and ArcNet. With the speed of today's equipment and networks, the usefulness of both these protocols has diminished. Carrier sense multiple access with collision detection. It's used by legacy Ethernet, operates in half duplex mode, where only device sends or receives at a time, and uses a collision detection process to govern when a device can send and what happens if multiple devices send at the same time. As previously discussed, if there is a collision, a jam signal is sent out, random timers are employed, and the first host whose timer has run out is able to transmit after performing a listen before send operation. Wireless uses carrier sense multiple access with collision avoidance. But in the collision detection process, devices transmitting simultaneously will result in a signal collision on the shared medium. On Ethernet, this is very easy to see because the voltage levels will change. The devices will detect the collision and then, after the jam signal, wait the random period of time and then try to retransmit the data. Carrier sense multiple access with collision avoidance. This is used by the 802.11 wireless LANs. Again, it operates in half duplex mode, where only one device sends or receives at a time. There are now devices that will also do full duplex, in that they use one frequency for sending and one frequency for receiving. It uses a collision avoidance process to govern when a device can send and what happens if multiple devices send at the same time. When transmitting, devices also include the time duration needed for the transmission, and other devices on the shared medium receive the time duration information and know how long the medium will be unavailable. Because all the devices have received this time, it is possible that multiple devices then try to send data at the same time. The data link frame has three parts: the header, the data, and the trailer. The data is not only the good put, the actual data that we are trying to transmit, it also includes the layer 4 and the layer 3 IP header. When it comes down to layer 2, it is just seen as data. We then put on the header, which will include with Ethernet a source and destination MAC address. We will also put on a trailer, which will have a frame check sequence, a mathematical way of checking to see if the frame was corrupted or changed during transmission. Some protocols do not use MAC addresses. Some do not need this, such as a point-to-point, because the sender puts data onto the link and there is only one place that it can go. So there is no need to identify the receiver. It is the host connected to the end of the wire. Depending upon the technology that we use, the amount of control information carried within the frame varies according to access control information and logical topology. The first packet in a communication stream going point to point may have all the information. Packets following that, or frames following that, do not need all the information that the original frame had. We can therefore speed up information or the transmission of data by eliminating some of that overhead. As we can see here, in the header, we have a frame start, and this will identify the beginning and end of the frame. This may be very simple, such as in binary AA or 55, giving us a combination of ones and zeros, which also detects our timing or gets our timing down. At the end of the start and stop frame, it may go from a single one to two ones in sequence, therefore notifying the system that the next piece of data is part of the addressing. The addressing here is layer 2 addressing, media access control addresses, 48-bit MAC addresses in Ethernet. We may also have a type field. This would identify what layer 3 protocol, either IPv4 or IPv6. We may have a control field, identifies flow control services. This provides us quality of service. The data, which would encompass not only the data that we are trying to send, but the header information from both layers 4 and layer 3. At the very end, a field used for error detection. And then another frame to say this is the end of this particular frame. Layer 2 addresses are referred to as a physical address, and they are contained in the frame header. These are used only for local delivery of a frame on a link, and they are updated by each device that forwards the frame. As we can see here, the original source, NIC, would be the MAC address of PC1. It would be sent to the MAC address of the input of R1. When it exits R1, assuming that this is an Ethernet connection, the MAC address, the source, will now be the exit interface of R1. The source is no longer the original source. It is coming from the router, so that is the source. The destination MAC will be the incoming port on the next router. After processing by router 2, the source MAC will be the exit interface of R2, and the destination MAC will be, in this case, our final destination. All through the process, the layer 3 information remained the same. The layer 2 information changed with each hop that it took from source to destination. The logical topology and physical media determine the data link protocol that we would use. Therefore, Ethernet, 802.11 wireless, point-to-point, HDLC, high-level data link control, frame relay, and many others would have a different set of protocols and sequencing when they send data. This concludes Chapter 6, dealing with the data link layer.